to Sid Nagel. I have the privilege of doing my PhD in Sid's lab, and Sid is definitely not another goddamn theorist. Sid is an experimentalist who has worked on all manner of really gorgeous experimental systems. He's worked on glasses. He, along with Andrew Liu, is a founder of the field of jamming, and really they were the ones who introduced the notion of the link between glasses and jamming. But he's also worked on beautiful experiments like coffee drop drying, which you may have seen whenever you've spilled coffee. Also, lots of liquid experiments, and all of the work is marked by a real attention to aesthetics and beauty, and an ability to reveal deep insights within
Okay. Enough. Okay, there we go. Okay, so should I start now? Thank you. Thanks, Eric. I guess just to start off, so I can get my bearings for who you are. How many of you are theorists, and how many of you are experimentalists? So theorists first. And who are not theorists? Okay, so there's a few real people, and then a lot of other people. Okay, so what I'm going to talk today, I'm going to start off these lectures. I guess I was asked to fill in something for Andrea Liu, who couldn't make it here, and talk something about jamming. And so I will start off with jamming and try to bring, at least give an overview of at least the beginnings of that field and some of the things that are important there. But then I want to turn my attention to various kinds of experiments. And so the original title that I was given for this was Experiments in Marginality. And of course, being paranoid, I thought this meant marginal experiments. And I got very nervous. But actually, when I started thinking of Experiments in Marginality, I thought, oh, that's a really good title, because it's a different way of looking at all of these different things and bringing them together under one rubric, which is, I think, quite attractive. So let me just tell you, start off with what I'm going to try to do in these lectures. So I'm going to start off by talking about jamming basics. And then I'm going to be talking throughout from this and then through a bunch of other, after this is over, I'm going to be talking about various experiments through here. And so the experiments that I'm thinking of highlighting throughout this, and so this will partly be during the jamming part, but elsewhere as well, is experiments on how to get RCP and coordination number. A very classic experiment. I want to talk a little bit about how you get the pair distribution function G of R in colloids and what came from that. I want to talk about robots and how that's related to marginality. I want to talk about some experiments on auxetics and allostery. And a year or so ago, I didn't even know what these words meant, and so I will have to explain what they are as we go along. So if you don't know what they are now, I will explain it when we get to that point. Then I want to talk about memories in matter. And then what I mentioned at the end of David's lecture was the dielectric constant epsilon of omega in glasses. Then distribution of forces and crumpling. And all of these, oh, and if I have a chance at the end, avalanches. But so I don't know how much of this I'll be able to get through and describe all of these things, but I want to give you at least a flavor to begin with what, some of the kinds of experiments that we can start looking at to study systems that are in this somehow marginal state. So I went to the web link and I listened to Gilles Tarjous's talk to hear what he had said about, in his introduction. And he talked about the glass transition. So now I'm getting into the jamming part. So I'm now here. This is where I'm starting. Okay, so he was talking about, so Tarjous lecture. So he was talking about the glass transition. And I want to be a little bit provocative here and try and say, okay, so he told you about this, and we've heard lots of lectures about this. I mean, David's talks were just about mode coupling theory for these transitions and so forth. But it was a transition that somehow everyone thought was very important. And what I want to remind you about is that, well, how did you get this? Well, you supercooled. Very, and I'll underline very, slowly. And if you were able to bypass nucleation so that you didn't get into this problem of nucleating a crystal on the way, then you would get into this glass state. So what you were trying to do by doing this very, very slowly was remain in equilibrium or quasi-equilibrium with the liquid state. So, of course, the crystal is the true equilibrium state of the system once you've supercooled it below its melting temperature, or freezing temperature. But below that, then the system doesn't realize that it should have become a crystal, and so still looks like a liquid. It's just a more and more and more and more sluggish liquid as you go down. Okay, so what are some of the best experiments that you could get there? And so you get Tg is the temperature at which you've fallen out of equilibrium with that state. That is, the timescales have gotten so large that you cannot continue to rearrange or continue to do the experiment and have the system equilibrate during the time of between one temperature step and the next. So Tg is where you've fallen out of equilibrium with this liquid state, and that you are no longer reversible in the sense. And the thing that you're greater than 40 degrees Kelvin above T0. T0 is where the dynamics gets arrested. Okay, so Tg is where you fall out of equilibrium, and T0 is where it looks like if you extrapolated your relaxation times in some way, which is always a problem, but you try to extrapolate it as best you can, and you find that there's some place at which it looks like the relaxation times have gone to infinity. Your Tg, you're 40 degrees Kelvin away from there. You're not close at all. So you can begin to ask, well, is the glass transition truly important for understanding the properties of this new state that you've fallen into? And look, I mean, I spent a lot of time taking that point of view, but now I want to take the other point of view just for the moment and say, well, look, if you ask how large have any of these correlation lengths gotten in the time scale or at this temperature, what you find is that the correlation length is a few angstroms. Only a few particles somehow seem correlated with each other, even as slowly as you've been able to go. And so this makes you wonder, well, look, is this really, if you want to understand the properties of the glass, is it important to really understand the glass transition? And I'm saying this in front of all these people who studied the glass transition, so I'm just waiting for them to well, I don't know what you do here in Colorado, but you throw things, I guess. But anyway, that's the thing that I'm now going to challenge. I'm saying, well, okay, so maybe the glass transition itself is not the most crucial thing if I want to understand glasses. So what is the thing that you do? What happens as you do form a glass is once you've gotten past TG and you've gone a little bit below TG, whatever your time scale is. I mean, you can wait hours, you can wait weeks to cool this thing. I mean, in some cases we've waited months to let this thing cool. I mean, there are now simulations which you can do even better, but you still aren't getting to the point where you can really get to the transition. And so do we care about the glass transition, or do we care about the sudden quench? Or is it the sudden quench that matters? That is, the sudden falling out of equilibrium, and then once you've fallen out of equilibrium, the system can no longer remain. It's stuck where it is, and that's the physics that you want to understand. And these are two different approaches that may be related, but I want to take the point of view in these lectures, well, this has got physics in it too, and this is a physics that I think is perhaps the place where we're going to understand the properties of glasses. Okay, now, I don't know about the rest of you. I mean, why are you interested in glasses? I mean, for the students here, is it because your professors told you to? I mean, maybe that's the thing, but I guess I'm always, you should ask yourself that. And when I was a kid, I was told, well, you go to the window, and you have this thing here, and I was told that's a glass, and that's different from any other material you have in your kitchen. So, what kind of nonsense is this? I mean, look, it's hard, and a piece of quartz I can see through too. That's a crystal. What difference does it make? And so, of course, what the difference is that you can take this to an X-ray machine and put in the X-ray machine and look very carefully and find out, oh, the atoms are not in an ordered arrangement, they're in a disordered arrangement. But why does that matter? If that's the only difference between a crystal and a glass, who gives a damn? Oops, I'm on record. Who cares? Okay? I mean, who cares? It's only if somehow the properties of this material that in this glassy state, in the disordered state, is somehow different from the properties that you would have if it were a ordered system, that then you say, this is an important question to understand. And so part of what I'm going to be trying to push here is say, if we understand something about this new state of matter, not new state of matter, but the state of matter that has to do with falling out of equilibrium, into this disordered state, that this actually has new phenomena, physical phenomena associated with it, then, okay, that becomes something that is really worthwhile understanding. Okay, so that's one. That's the preamble to this. But there are other issues. And so what are they that come into this that are interesting physics questions? Well, one is what I've just said, order versus disorder. And what I want to point out here is that when you're taught solid-state physics in your first class in solid-state physics, and maybe even your second and third and fourth classes in solid-state physics, what you're taught about is crystals. You start off, they give you, I don't know which books you used now, but Astroff and Merman or Cattell or any of these common textbooks, they start off with a perfect crystal, and they tell you how to understand the behavior of the perfect crystal. But, I mean, nothing that I see here, none of this stuff is a perfect crystal. And so what is the next chapter about after they've told you about perfect crystals? They tell you about defects. And so you can add a defect here and you can add a defect there. And that, there's physics of defects, and it's a nice place to start. You have this perfect crystal ideal system, and you can work around it, and you're so you get perfection there, and you can add defects around that and see what it does. But no matter how many defects you add, from that point of view, you can't get to the glassy state. That is, the physics of the glassy state is not just an agglomeration of individual point defects that you put into the system. It's somehow different. And so this is one of the issues. So a glass is not equal to lots of defects. In a crystal. Okay, so that's one issue. A second issue that's a wonderful issue to think about is equilibrium and far from equilibrium. And again, one of the things physics is great at is studying systems in equilibrium. I mean, as I've told lots of people, you can take a box of gas and you can bore anyone completely stiff by telling them all the properties of the box of gas, because you can understand it, because it's in equilibrium, and you can calculate everything you care about that. But most things in life are not in equilibrium, and so how do you begin to address those kinds of questions? And so that's one of the things that comes into this issue of glassy phenomena and systems that are marginal. Yeah. I'm sorry.
Is there a difference between a liquid and a crystal?
Well, certainly in 3 dimensions, I would certainly claim there are. In 2 dimensions, yes, there is, KT, N, Y, H. Thank you. Theory, and so so there is a region where you can actually think about that transition, but what it doesn't tell you about is, well, what happens in the solid state. That is, if I want to ask questions about rigidity there, understanding that transition takes place isn't helping me particularly there. Maybe it can eventually, but I don't know that that's actually been done yet. I mean, so that could be my ignorance. Okay, so and so I just want to point out here that when we talk about far from equilibrium behavior, there are 2 ways of doing this. And they're distinct. I mean, one is that you continually add energy to a system so it can never get to equilibrium. That is, as long as you are putting energy in, then the system is not in equilibrium. So a flowing system, for example, or a turbulent system, I'm injecting energy and it's not in equilibrium, and wonderful dynamics happens, and that's one way of getting far from equilibrium. So this is injection of energy. And the other way is the one that has to do with glasses, which is that you're not injecting energy, but your thermal energy in the system is too small to allow for the things to relax. And so you get stuck in states that are far from the equilibrium states that you would have been able to access if you weren't far from equilibrium. And so glasses and jamming are really the epitome of this second type of falling from equilibrium. And so that's the top one would be all having to do with nonlinear dynamics and chaos and all of those things, and that's not the subject that I want to talk about here. The third thing I want to just say here is nature of rigidity. And so you know that you have a rigid system like these metals, which are polycrystalline, that you know something about why those have formed and become rigid. Is that the same kind of rigidity that you get for an amorphous material, a piece of glass? And there's no reason that it has to be, but if it isn't, then what is the relationship between them? What new kinds of things happen with the being far from equilibrium and the onset of rigidity in these different kinds of systems? Okay, so that's what I want to say for the background of this. And so now I want to talk about, well, what is the idea of jamming? So the idea of jamming is to is another way of constructing a solid. Okay, that is different from crystallization. So we understand something about crystallization. That is, we know that you take this liquid and you supercool it below its freezing temperature, and then, except for this one case in 2 dimensions, what typically happens is that you get nuclei of the crystalline phase form, and if the nuclei are big enough, then they start to grow and envelop the entire system, and that's nucleation and growth phenomena. Here, this is a very different way. And so what do we want to do? Well, what we want to do is look at this way of forming a rigid sample and see what it does. And so it's an ideal system. Which means lots and lots and lots have been left out. Okay, and so that's and so I will try to indicate a few of the things that have been left out near the end of this, but I'm really going to try and just think about the spherical cow model of this by thinking about spherical cows. Okay, so what is the idea? So I'm going to start off. We can take whatever dimension you want, and so we take d dimension. And so in this d-dimensional system, I take a box. I'm not going to write this in, but it's easier just to show. So I have this box, okay? And boxes of some fixed size. And I take spheres, which are hyperspheres. So if you want to be in 2 dimensions or disks, in 3 dimensions or spheres, whatever you want. So they're nice spherical objects, and I just stick them in this box at random. And they are at random, so they can overlap with each other. I mean, I'm really doing this thing totally at random. So I take this random thing and put these n particles in this box. And the thing about these spheres is that they don't see another sphere if they're too far apart. So so if 2 spheres are not overlapping, if they don't touch, they are no forces on them whatsoever, no interactions. They only have interactions if they start to overlap, and then the interactions are very simple. They just try to push each other apart. Okay, so it's a repulsive finite range interaction. Okay. And for simplicity, and this is a big, big, big simplicity, is no friction. And that's one of the big things that has been left out if you want to understand real systems. And there's been a lot of more recent work has been trying to study friction in these models, but I'm not going to say too much about that here. Okay, so what kind of potential do we have for this? So V of Rij, where I and j are labeled the particles, is going to be some energy scale, epsilon, over this number alpha, which I will tell you in a second, 1 minus Rij, which Rij is the distance between the 2 particles, divided by sigma Ij raised to this alpha particle. So it's the same alpha here and there. And then this is times a delta function of Rij. I can never remember whether it's so this acts when they're too close, and it's 0 when they're too far apart. I mean, so I'm going to just try this. Is that the right one? Other way around. Other way around? Good. Okay, so that means that if 2 particles are too far apart, they don't see each other. The potential is strictly 0. And if they're close enough, then the potential starts to rise from 0 in some kind of power law fashion. And we can vary that power law. So if alpha is equal to 2, this is just repulsive springs. Okay. If alpha is equal to 2, alpha equals 2 is repulsive springs. If alpha equals 2.5, this is Hertz. Hertzian potentials, that is, that's 2 elastic spheres that just try to overlap in 3 dimensions. And so there the repulsion, or the spring constant between these 2 spheres gets bigger as there's more overlapping area. And so this is the behavior for that. And alpha equals 0 in here would be hard spheres. And so that's why the alpha is here, just so that it really would go into that limit if you took the alpha equals 0 case. Okay, so this is the potential that we have. And so we have this potential, and then we try to do the following with as little dynamics as possible, but of course there are dynamics. And so if these particles now are put in at random, they overlap. At no point is the energy diverging here between 2 overlapping particles. So this is like starting with the t equals infinity system. That is, they're totally random where you put them down. And then the next step is you quench the system to t equals 0, and you just drain the energy out as rapidly as you can. And there are lots of ways of doing this. And so the second thing is drain out the energy. Okay, and so you can do this by steepest descent if you want, or you can do a conjugate gradient, or you can use the fire algorithm. You can use all of these different wonderful techniques to get you to the lowest energy state as quickly as possible. You're not letting what the effort here is that you have this very rich and complicated energy functional system, and once you've landed in one point in this by placing these n particles in the box, then you want to just go to the nearest local minimum. And so that's the idea of this, that you're not giving it any extra energy to cross over from one energy to another. Now, you could do that, and you can do that on the way as you cool this thing, and you'll get some properties which are a little bit different, but basically it doesn't make too much difference in terms of the things I'm going to tell you. So there isn't just going to be one point you get to, but a line of points which I will mention. Now, when you do this, you're going to get two things. You're going to get either a state in this box. Can people see down here, or is this too? No. So where it's too loose, so the density or packing fraction phi is less than phi c, the packing fraction where this thing would freeze up. And so this would be an unjammed configuration where the total potential energy in the system is 0, the pressure is 0. That is, if it's at, I should also say, once you're at, so you reach t equals 0. So everything here is in the t equals 0 limit. And so that means that there is no dynamics, there's no thermal contribution to the pressure. And what's really important is this makes the simulations clean. That is, because you don't have to ask, is this thing changing into a new energy well while you're doing it? That's not going to happen here unless you perturb the system, and then that's what you're studying. But you don't have thermal excitation into these new states. And so that's part of what makes this, why you get to say really clean things about this simple model. If you're at etc. So phi is greater than phi c, then the particles are forced to overlap, and you get the system that is now jammed. That is, the system cannot find a place where the energy goes to 0, and so these particles are forced to overlap with one another because the density is high enough, and so the system is gets stuck in that state. Now, everything that we do is, to first approximation, is that we measure everything with respect to the phi c. So phi c will change a lot from one configuration to another, to another, to another. And so looking at the distribution of those phi c's is one thing you could do to ask what is the thresholds for the jamming threshold here, and that will depend a lot on size and and perhaps on your algorithm to get there. But the other thing we also do is that there are going to be some cases where there's a particle here that is not have to touch anything else. Those are called rattlers. And we take those out of the system and don't consider them as part of the backbone of this. I mean, you can keep them in and look for some properties of this, but for most of the stuff, that's not the most crucial thing. Okay, so this is the what the model is, and so the question is, what does this give you, and what's happening at phi c? And so I said perhaps the understanding the glass transition isn't necessarily important for understanding the properties of the glasses, but this is a different kind of a transition. This is not having to do with temperature. It has to do with staying at T equals 0 and changing phi from low phi to high phi, and you go from an unjammed state to a jammed state, and there you can say, well, what is that transition? And if I understood that transition, does that give me a place to stand that's opposed to the case of pure crystallinity? Pure crystallinity is ideal. It's perfect order. You can't get any more order than that. Is phi c the opposite extreme from that, where I can't get anything more disordered from that? And so that's what I'm going to try to argue in some sense. I mean, there's lots of ways that we might want to talk about disorder, but at least in some sense, it is a place where you won't get it's as disordered as you can be. Okay, so now I wanted to ask, so what is this phi c? Okay, so this goes into a packing problem, right? This is how can you pack spheres in d dimensions. And in 3 dimensions, this has a very long history. I mean, this goes back to the time of Kepler, who and his dates were 1571 to 1630. And so the densest packing you could make for monodispersed spheres in 3 dimensions was, he hypothesized, the FCC lattice. So phi is something like 74%. Okay. This, was his guess. It was a hypothesis. And it became Hilbert's 18th problem. I don't know what they call it, century. Well, 100. I mean, he did this in 1900, so it was the problems they thought would be very important for the next century of mathematics, and it finally got solved in 1998 by somebody named Thomas Hales. And yes, it is. And my reaction to this is, well, yeah, but I knew that. I mean, it's not so. I mean, once you start looking at the FCC, you realize, well, there's not a better. You can't do any better than that. Obviously. I mean, kind of obviously. I mean, it's so obvious you don't think you need to prove it. But in mathematics, you have to prove it. And so it took a long, long time to prove it. But what is a question which is less obvious is what happens when you have a disordered system. And this was addressed roughly around the same time. So this is by someone else, not Thomas Hales, and no relation, Stephen Hales. And he was 1677 to 1761. And he was an English cleric. And he asked 2 questions about this. One is, what is disordered packing? Disorder. Density. And what is the coordination number? These seem, at least the second one seems a much more modern question than the first. And so how did he address this? And so this is the first experiment that I want to tell you about. So he wanted to find out what is the disordered packing density, what do you get for that? And so, it's a experiment that, we kind of might have gotten on a very good day. We would have figured out how to do this. And what did he do was, well, he took a pot, and he took a bunch of peas, which are nice spherical particles, and he poured them into the pot. And then he poured water into the pot till he just covered the peas. And so by knowing how much water he put in versus the volume of the pot, you could figure out what the density of those sphere packings were, this disordered sphere packing. So, it's a good experiment. I mean, I'd fund it, but if it hadn't been done already. But so that's good. But then he asked the question of, what is the coordination number? Now, you think about that, and, whoa, how are you going to do that? And so this is what I want to say is the power of a great experiment. I mean, this is one of my all-time favorite experiments, bar none. It's up there with G-2. I mean, it's really because it is elegant and gets to the essence of this problem easily. So what did he do? He had peas, he had pot, he had water, and he had fire. And so what he did was he covered the pot and lit a little fire underneath, and so that the peas expanded ever so slightly, and then turned the fire off. They expanded slightly so that now they ran into each other, and they created little dimples where they pushed into each other. So he didn't have to go in and look at this, how they were connected. All he had to do was take the peas out and count the number of dimples on each pea, and that gives you the coordination number. Now, that is it's up there, right? I mean, it uses no more than, yeah. I love it. Okay. So this is written up in a book that he is called Vegetable Statics with a K. So, not only does it get the greatest experiment of all time, but the best title. It's a great thing. Okay, so this is that first experiment. It's hard to find the data, but at least he laid out how you would do this. Okay, so this is the first of the experiments I wanted to point out, is that these are the kinds of experiments that you can do in a marginal system. The other thing I should just quickly point out is that this history of what we've done with the jamming of, having particles that only interact if they're repulsively, but don't have any attractive interaction in them, is not anything new with jamming. This is something that goes back to the theory of liquids. Weeks, Chandler, and Anderson talked about this and about why the attractive part of the potential is really just a perturbation on the important part, which is the repulsive part of the potential. And so they have this if you take the Leonard-Jones potential that we've been, I know David talked about it, so you've heard about it. It's just this 612 potential. It has a potential that looks basically like this. And if you ask, well, what's the most important part of this whole potential? Well, the biggest part is this part here that's repelling each other. And this attractive part is rather small, and it just keeps things close to each other so they can feel the the repulsive part. And so putting it in a box with just the repulsive part can mimic very much of all of the behavior. And so that's where this is, some of these ideas come from for the jamming. And so what you basically do with this is you erase the attractive part, and you just have the potential stop there, and just raise it up so that it's goes to zero. There's no discontinuity in the potential at the point of where it goes to zero. Okay, so that's how one looks at this. Okay, so then having said that, then what do we want to, where does this idea of jamming come in? Is the first thing was the idea of a phase diagram, which and so the idea here is that what we wanted to do was look and see, are there a variety of different systems that all seem to have kind of similar behavior in some way, but they're not all glasses, right? And so the idea here was to try and, try and step backwards and ask, okay, so what are the things that are kind of important for the jamming idea? And so if we have one axis being the temperature, then an axis, so here this axis is going out of the plane. This is the 1 over the density axis. And here what you would think is that, well, in this plane, this is just a glass transition plane that we're typically familiar with, right? You've got temperature out of the board towards you is 1 over density. So as you go to higher density, typically you'll have to go to a higher temperature in order for this thing to melt and be able to flow. And so you have a line that looks like this, and this would be kind of the TG line. But then there's another axis which is important for flow, which is how hard you're forcing this thing. And so in this direction, I have the shear stress in the problem. And along this shear stress 1 over density plane, okay, that's what we would have called the yield stress of a system. So this is yield stress. And so the idea is that, well, you put all these things together into this one diagram, and then everything near the origin in here is going to be jammed. Everything far enough away from the origin is going to be flowing. Okay, and so this was the idea of the jamming transition. So it tries to say, well, look, there are a lot of different control parameters that you might be interested in, not just temperature, but the way this thing is being forced. Now, this is one particular drawing of this, and I think, if you change the potentials, you might get a different drawing. The point of the phase diagram is much like you would do for an alloy system. So if you go to Hansen, which is the book of all alloys, the phase diagrams of binary alloys, the point is that they each have a phase diagram, but what you need to know is what are the axes of this thing. And so these are the three kind of axes that try to generalize the typical thing having to do with two of them at a time. Right? And so you might even be able to think of more axes that you would want to put on here, but I wouldn't be able to draw that in any simple way. Okay, so this is the idea of that jamming. And so, one question here that's come up is, if you had this phase diagram and then you added friction, what does it do? Right? And so this now will have a different phase diagram, but you would still want to somehow put it onto these axes to find out what, how does friction change the picture if you started with a zero friction, frictionless case to begin with. This point here is the jamming point. Okay, and this exists for potentials of this kind, where they're finite range and repulsive. If you have long-range interactions, this thing would not end at some point here. That is, at zero temperatures, they'd interact all the way out to infinity, and so this is only, that point only exists for finite range potentials. Yeah?
How does the point scale with alpha? Does it change with alpha?
Well, it doesn't change much, because at t equals 0, everything basically, once they touch, that's it. You're not really exploring what happens with overlap. Right? And so, so the nature of the potential, all that I cared about here was the fact that it was finite range and repulsive. I mean, if it's attractive, then you can get beads forming lines and so forth, which is a different problem. Okay, so one thing that now becomes important is this idea of constraint counting. And so this goes back to Maxwell. And there are a bunch of other people who have looked at this in more recent times. So these would be Jim Phillips, Michael Thorpe, and Shlomo Alexander. But I'm just going to talk about the simplest situation here, where I have spheres. And what Maxwell asked was, what do I need to have something be rigid? He was interested in bridges collapsing. And so he wanted to know what was the minimum number of ingredients you had in order for this bridge not to collapse. And so what he says, so if I have spheres in d dimensions, what do I need is I need that all the spheres are in mechanical equilibrium, so that there is no there's no net forces on any particle in the system. So how many different equations do I need to write down in order to satisfy that? So if I have n spheres in d dimensions, that means that there are n times d equations. Right? That is, every particle has 3 dimensions it could move in, or d dimensions it could move in, and there are n of them, so that's the number of equations I'm going to have to satisfy. And then you ask, well, how many constraints? And so these constraints go back to the question that Stephen Hales talked about, which is, what's the coordination number? And so if every particle, what's constraining this is there's is the fact that other particles are hemming it in, and so that's the coordination number. So if there are n particles, there are nz coordination number, but I've double counted, right? Because each time I have a coordination number, it's the same thing between the two particles. So it's really nz over 2 is number of constraints. And so Maxwell's idea of what is the minimum number I need is when these two things are just equal. So nd is equal to nz over 2, which implies that zc, the smallest number, is going to be 2 times the dimension of space. And this is, I'm not thinking about finite size effects if I don't have periodic boundary conditions and so forth. This is just the simplest case that I can write out for you. Okay, so this is basically a universal number for all of these jam packings. This is where you have to end up, is at the jamming threshold. If this thing is just minimally stable and just manage to get the last contact in order to prevent it from having zero frequency modes in it, then this is what you have. Z is 2 times the dimension of space. So that looks pretty trivial. But let me give you an example. So in 2 dimensions, I need 2 times d, that's 4 coordination number on average. Okay, so here's one particle, and I put another particle here. I put another particle here. Put another particle here. That's 3 particles, and I can't move my head. So what went wrong? No, there's no friction here. I mean, I'm just got, this is 1, 2, 3 particles. They're just repulsive particles. I can't move, my head can't move. Well, but I mean, so all these other things could be whatever I wanted. No, I mean, I've just enough so that these forces all balance here. So, look, you know, it's a trivial statement what I just told you, right? I mean, it's hard to argue with it. But what is the crucial thing here is what I just gave you this example, that was local stability. Local stability. This was a global statement. This is about the entire system. So there's a big difference. I mean, 3 is not equal to 4. The criterion for local stability was 3. For global was 4. So the local stability is easier to achieve than the global stability. So this is, you know, from my point of view, so it seems so trivial, but then you stop and you think about it, and you get really upset by this. I mean, I was upset for, I'm only experimental, so what do I know? But I was very upset by this. I mean, this was not the way, I didn't really fully understand. And what I think is, from my point of view, going from the local to the global, in some sense, is where a lot of the bodies are buried in this whole problem. Is how do you go from local to the global to be able to make all this work? Okay, so this is, and so you do these simulations and you get these numbers. I mean, so that's fine. Okay, so now what I want to do is, okay, so what do we see happening in this? So that is, suppose I'm in an unjammed configuration. So all the particles can't, I just said that they push each other apart. But could I have 2 that are overlapping in here, for example? So, here, my head is one. Okay. So could I have this happen in the unjammed state and have this overlap? And the answer is no, because they just push each other apart. Right? That's what this would say. Okay. So then, but then I just hold this in place by putting another particle here. So is that stable? And the answer is no. They would push each other apart, then this thing could move, and the whole thing would be unstable. So I can't have anything, I mean, below the transition. So if I plot Z, the coordination number, below the transition where the coordination number is where there actually any overlap whatsoever, it has to be strictly 0 till I reach phi c. And then at phi c, what happens is that these things suddenly span the entire volume of my system. And so this thing shoots up to zc, which is equal to d, which I just told you. So it shoots up to this universal value. And then what happens is I go above this. Well, now I can continue to compress this system, and z continues to rise as particles start to overlap, and more overlap as I increase phi above that jamming threshold. Okay, so this is a smooth behavior, and this is discontinuous. And this is smooth part. So if I plot z minus zc, and now I do this on log scale, what you see is that this thing is a very nice power law with a slope of a half. Well, I'm sorry, this is experiment, therefore I'm not allowed to write integers. Okay, there will be error bars associated with it, right? Okay, so no, it's so this one is always a half. Okay. So this is now looking a little bit bizarre. So I have this critical point or phase transition between jammed and unjammed. They all seem to have this behavior. There's a discontinuity and then a continuous part. And then I can ask, okay, so let's look at other things, which now getting back to the rigidity part. And I could ask, okay, so what is the pressure versus phi minus phi c? The pressure is 0 below phi c. And then above phi c, it starts to increase. I do this with a log. And now this, again, has a nice smooth power law. And this has the one that, Eric, you're thinking of. This has a slope of alpha minus 1. That is, it depends on the potential. And this is what you would expect, because look, what is pressure? It's what's pushing back on me. So if I squeeze all of this thing, what am I paying? I'm paying the potential energy of these things overlapping, which is going as phi to the alpha. And so I'm taking the first derivative of that to get the pressure, and so that's alpha minus 1. So the bulk modulus would have been p to the alpha minus 2. I'm sorry, it would have been delta phi to the alpha minus 2. I'll just draw that just so that we and that's what you would expect. That is, the bulk modulus is the second derivative of the potential. That's typically what you expect for a modulus to be. How about the shear modulus? So the shear modulus, what do you do with the shear modulus? So you take your system and now you shear it a little bit. I'm sorry. You measure the energy that it takes to shear this. And so what would you expect? Well, these particles are going into each other maybe at an oblique angle at worst. So there'll be a cosine theta associated with how these particles are moving into each other. But as far as the dependence on the potential, it should still be the same thing. It's still the same potential, and you're just coming in at some different angle with respect to that. So you would have expected the shear modulus G versus log of phi minus phi c to also go as with the power of alpha minus 2, and it doesn't. It goes as an anomalous power, 1.5, but alpha minus 1.5. Okay, so this is normal, this is normal, this is abnormal, for those who like Mel Brooks. Okay. Okay, thank you. Like Mel Brooks, okay. So this is something that needs to be understood more. But what this tells you is that if I look at G over B, this is 1/2. And so this is something now that which makes these solids, this kind of rigidity, different from the rigidity of a crystal. So if you remember what I told you about this rigidity, is it should go as alpha minus 2, the shear modulus, and that's what every crystal does. And what this is, and so as you lower the pressure on a crystal, the ratio of G over B doesn't vary. G might vary and B might vary, but they vary in tandem so that their ratio stays roughly constant. So all crystals have roughly the same ratio of G over B. I mean, it's a third plus, they're of order unity. I mean, there's a cosine theta, but that's basically the kind of thing that you will get. And so it's not, they don't vary by orders of magnitude. This is saying that as I go to the transition point, this thing, by orders of magnitude, goes to 0. Okay, so this again says that this is a weird kind of transition. I have all sorts of things. I mean, it may not be exactly understood, this and this being alpha minus 1.5, but these are scaling, and this is discontinuous. And so Z, being this most important quantity in the system in some sense, is a discontinuous thing, but then above it, it becomes continuous. And so it still has scaling above it. And so this is a kind of a mixed order phase transition, and I think it falls into the same category of transitions as a p-spin Potts model. See, I said that. Did I say it right? Did I pronounce it right? Okay. So there are other things that have the same kind of a transition, but this system has it by itself. Okay, so I am running, yeah. So if I add friction, then so I don't really know what, to be honest, I mean, I don't really know what would happen if you add friction to this, that there will be certain things which would definitely change a lot. And the shear modulus, I mean, so there's a question of actually what point do you want to be adding it about. That is, so the phase diagrams that people have drawn, so there's the stuff that the Chakraborty and Berenger and then there's some more recent stuff by Viart and Cates. They tried to look at what is the effect of friction on at this level of the of it. So the question: so how much did you really get something happening at point J, or do you have? Is there a and becomes very complicated, and I'm not sure I understand it completely. So I'm going to just shut up before I make a fool of myself. Okay, so, but it's a very good question, and it's a very active question right now, trying to understand this, because if you want to apply this to study colloidal systems, real systems, you would better include something like friction to figure out what things are important.
I'm wondering if you have friction, like with elementals, jam packing be more common, and then like within any dimension, effective dimension.
No. So what happens with friction is that you have to first of all count differently. And what is ZC for frictions is not 2D, but it's D plus 1, because friction is now a constraint on the system. That is, you can't have transverse motion, so it's constraining that. And so, and then you ask, well, in real systems, do you ever get to the point where Z is equal to D plus 1? And you never quite get there. No matter how carefully you're trying to get this thing, you're always getting a little bit above D plus 1. So even the experimental part is, you get at different structures, but it's also because you're counting differently. And I should just point out one thing that I said here, which raises this question, which is you let me get away with saying, oh, well, I should say over here. You bought this argument, right? And the equations, NZ over 2 constraints. But how come I didn't worry about the spheres rotating? So this gets a little bit to your question about friction.
You can't constrain that.
Well, you think that's a obviously it doesn't matter, right? Just obviously. I mean, so that's what you can possibly care about the fact that these things are rotating because they don't couple to anything. Well, you better be careful when you do that, because suppose you just did the following tiniest little change on what I did. Instead of taking spheres, I now squeeze the sphere epsilon in one direction. So they are no longer complete spheres. They're slightly elliptical. Then how should I do the counting? Did everything I just said about spheres go out the window? I mean, I've only changed this by epsilon. I mean, the tiniest little fraction. I mean, less than an atom difference. I mean, but I mean, should that have made any difference? So the issue dealing with how do you really count the constraints is not trivial. That's what. And so that in that case, you should have counted every single rotational degree of freedom. I mean, that comes in there, right? I mean, that's a which you said shouldn't matter, but now it does matter a bit. But it only matters a bit. I mean, and so it's a question of well, how did I go from one to the other here? And is it a discontinuous thing, in which case spheres are irrelevant, or are spheres a relevant place to start, and then you go away from that a little bit, and you will perturb around the sphere case? And it turns out to be the latter, but it's not trivial to try and understand that.
I have a question about the maximum count. So according to the count, we say something is meant for rigid when the z is slightly like in order of 1 over n, more than 2d. So does that mean that you're considering a jamming point slightly above that?
Yeah, so this is where I said you have to worry about the finite size effects in the problem. So that when I've got things of order 1 over n, that's really saying, oh, I've got a finite size thing. So remember what this count was. I mean, so the way I think about it is a little bit of things that I've left things out and I've put things in. You know that if I had my system, well, it shouldn't have been just ND because I could have just moved the whole system up, or I could have moved it this way, or I could have moved it this way, costing no energy, and we wouldn't have said that that wasn't rigid. So I was really already off by dimension d, which would have come in the number of constraints that I have, or number of equations. And so that would have given me d over n a problem. So, but it's over n, so that's why I'm neglecting it. The other thing that comes into this is, well, okay, so I want to constrain the bulk modulus. Well, I only gave you enough constraints to constrain all the normal modes in here. And so the bulk modulus is one extra thing I have to constrain, and so that's a +1. So there's a -3 +1, then I have shear moduli, and so I want to constrain those. And so these are all of order 1 over n, they're the finite size effects. But that's where these effects come into trying to do this carefully. Okay, so I am way behind what I thought I would be at. So what I want to do is ask, okay, so what, so I want to get, so there, I've told you one thing that makes this glass, or this jamming system as a, you know, or this model at least of a disordered system, different from a crystal, is this fact that G over B is going to 0. And at the transition. And I should just point out, I will talk about this a little bit later when I get to it, but G over B is an important quantity just in and of itself, because that's what determines what's called the Poisson ratio of a material. It's just a 1-to-1 mapping between Poisson ratio and G over B, and I'll say that later, but that's why I stress that G over B is the thing that I'm going to be talking about. And I will get to that, so don't worry about that yet, but that's why G over B actually has a meaning here. So I can tune G over B everywhere in here. And so that's one thing that's different. But now there's something else. The second thing that I want to say that makes these things very different from a crystal is, what do you expect for the density of vibrational modes? Okay, so this is an old story of how you calculate this. It's really at the fundamentals of quantum mechanics where we first ran into this. And so what was the thing is that people had measured the specific heat of crystals, and you found that the specific heat goes as T cubed at low temperatures. Okay, so and if you think about this classically, it was very difficult to figure out how you could ever get something that went this way classically, because every classical oscillator, if every normal mode is just a harmonic oscillator in the system, every normal mode is equally excited at low temperatures, and so you should have just gotten the law of DeLong and Petit getting better and better and better and better as you go to low temperatures, so that C over T should have just done this. It should have gone to 3nk. It should have just been a constant. And the fact that you got this behavior is what was the second thing. So first we all learned about the Blackbody radiation. That was what gave rise to Planck's theory of blackbody radiation. But then Einstein came along right after that and gave an explanation for why T went to 0 at 0 temperature. But he got it kind of wrong. That is, it wasn't complete. Whatever you want to say about it, can't say he was wrong. He was always right, except for the Stokes-Einstein equation and this and a few other things, but basically right. Okay, so what was it that we were taught to do? Is this is Debye came in and told us how to calculate the modes of a system. What are they? They're going to be plane waves in a perfect crystal. And what he said is that the way you do calculate the specific heat is you want to know how many plane waves you can fit into a box. And so such that you have the boundary conditions, you choose your boundary conditions, but so you satisfy those boundary conditions. And so you have these plane waves and you fit them in the box and you just count. One thing we know how to do is we know how to count plane waves that can fit into a box. And so what, when you do this, the density of states is going to go as omega to the d minus 1. And it's this omega to d minus 1 which then gets put into, when you put into the thermal, how many you excite, gets this as a factor of t cubed in 3 dimensions. So this goes as omega squared in d is equal to 3. Okay. And this is what all crystals are supposed to do. And it's what all glasses are supposed to do too, right? That is, what is the, where at least how I was taught about this was that, well, okay, suppose you have a glass and you start putting in disorder into this system. Well, if you go to a long enough plane wave, you're just averaging in this plane wave the elasticity in this region, and the elasticity in this region that where it went down, and then the elasticity where it comes up over here. And at some point, when the wavelength is long enough, these averages are all the same. And so you regain elasticity on long wavelength. And so basically, the low frequency modes are always plane waves, and plane waves are always going to then average over the elasticity in that wavelength. And so the lower frequency you go, the longer wavelength you have, the better the averages will be. And so you should always regain elasticity in a disordered system. Okay, so what this depends on is that the normal modes are plane waves. And so what do the normal modes look like in a jam system? And so what I'm going to be doing is I'm going to be looking at along t equals 0 on this axis, and that's the only, no strain on this thing at all, so it's just along the t equals 0 axis. And I'm going to start off here at some point inside here where it's a rigid system, and I want to ask what does the plane wave, what does at the beginning of the next lecture, I will show what the wave actually looks like. I brought some slides to show pictures, but I don't have enough time to really show that, so I'll just flash it up next time. But it's definitely not a plane wave. It looks like this swirly thing all over the place, but it doesn't seem to have any particular plane wave-like character. And so So there's always going to be the highest frequency mode in the system. That's where these particles are going in and out of each other as rapidly as possible. It's going to have a peak here, and then it's going to drop off as you go to lower and lower frequency. Okay, so that's deep inside the jam phase. Okay, so now I'm going to move a little closer to the jamming point. And what does this thing look like? Basically looks like that. And then I move a little closer to the jamming point, and looks like this. I move closer still, looks like this, looks like this. That is, if I plotted this on log scale, so log it does something down here. I don't know exactly what. I'm not going to, I don't particularly care. It's just falling off from this. That's as you approach phi c, as what you get is that the density of states looks constant all the way down to zero frequency. Okay, and so this is, again, behavior which is extraordinarily different from what you get from a crystal. And it's different, certainly, at the transition, in the same way that at the transition, G over B was 0, and not a constant the way it is for a crystal. But here, you also see that as you compress the system, so the fact that you have this phase transition, this critical point at phi c, it controls behavior in its vicinity, just like any good phase critical point should do. That is, it still has a plateau. It's just that the plateau doesn't go all the way down to 0 anymore. There's a cutoff. And so omega star is where this cutoff takes place. That is for any frequency. So omega star measures end of plateau. The frequency at the end of the plateau. And it depends on the pressure or the density that I have. So I can plot omega star versus phi minus phi c. And you get a nice power law with this, again, that can be fit with a power of a quarter of the, I recall, of a half, sorry. Yes. So that means as I approach phi c, I have more and more modes down at lower and lower frequency. And so you see what's happening here is that there's no remnant left at all of the Debye scaling. Debye scaling on this plot would have been, that's Debye. And this is saying, oh, I've got gobs and gobs and gobs of states that are lower frequency than I would have gotten from plane waves in the system. Okay? And one of the things that I haven't been saying too much about this is that these things don't depend much on dimension, at least 2 and 3 dimensions. I mean, the stuff that we've looked at, it's the same in 2 dimensions and 3 dimensions. And same with G over B, it's same in 2 dimensions and 3 dimensions. These things are not dimensional dependent. And so what this makes you think is that if this is a critical phenomena of some kind, 2 dimensions looks to be the upper critical dimension of the system. And there's arguments, yes, no, yes, no, yes, no, which are far beyond my understanding of the subtleties of that, but certainly this kind of behavior is certainly suggestive that that's the kind of thing that's happening here. Okay, and so yeah. So this is what I want to show you a picture of at the beginning of next time. I mean, well, I can show it to you. I mean, I'm out of time right now, so I know I can't spend a second longer here. So I will, if you want to see, I can show it you now, but I will show it to you at the beginning of next time, so at least you see what this looks like. That is, it doesn't look like plane waves. They are disordered things that are essentially, most of them are just extended throughout the system, and then the very, very lowest ones look to be, I'm very wary about using this word, but quasi-localized, in the sense that we know that if they hybridize with plane waves, they can't be completely localized, but but they certainly are. The language that I was taught, I would have used the word highly resonant modes down there. That is, that they really are very strongly around one set of atoms in this system, and then very low excitation everywhere else. So that's what they look like, but I will show you some of those pictures next time. Okay, and so I guess I stop now.